you for joining today's session. There's a QR code where if you scan, it will just basically take you to the GitHub repo. This is the GitHub repo. Sorry, it's a bit small. So I think there's a repo called Search Engine Workshop, and when you go to it, there's a link like Jupyter Hub. If you click on that, you'll be taken to the environment that has all the dependencies installed for today's session. So yeah, this is the. We will come back to this again a little bit later when we go to the first notebook. So if you miss this, that's fine.
Could you write down the URL maybe on the board? Yeah.
Sure. It's also the easiest hub.nc.training. And we'll come back to it again a little bit later. Cool. So, what is the agenda for today? So we have about 4 topics that we wanted to cover, and we have appropriate notebooks for that too. So we want to talk about sparse embeddings, dense embeddings, ANNs, and some things we want to consider for production use cases. So Ravi and I are machine learning engineers at Walmart Search. So feel free to reach out to us later. So what is the history of building a search system? I would say in the last several years, there have been about 4 maybe milestones, I would say. So the first thing is regular Boolean matching. It's a very simple system, and you'll see how simple it is. The next system is instead of just using simple tokens, can we try to build a simple language model that considers how often a term occurs in a document, how often the term occurs across the corpus, things like stemming, stop words. So that took a lot of time in the research community. And then in 2000s, once we started getting large web traffic, there was a lot of research that was spent on things like learning to rank. We started seeing in 2012 things like word to vec. And then in the late, let's say 2014, 2015, with the start of things like BERT, we started seeing vector-based retrieval. So those are how I would kind of group the 4 areas in the timeline. So let's start with token-based retrieval. So let's say you have a query like pictures of kitten legs, right? So the first thing you might do is you might tokenize it. You might tokenize it by white space. So you have 4 tokens here. But then maybe you might remove stop words. So words that occur pretty commonly. So in this case, maybe off might be removed. The other thing you might do is you might stem the tokens. So instead of plain, you might use play. So now you have 3 tokens. So now you look at your corpus and you try to see which of these documents have most of the words. So if you look at the first one, images of cat playing, it doesn't have the word picture, but it has images. But because we're using a pure token or a word-based approach, we don't really match the intent there. If you take a look at the last document, the document is pretty long. It has a bunch of words there. It technically has all the words that we're looking for, but it doesn't really seem to match the intent. But based on this approach, if you're just considering how many of the tokens match, document 3 would be considered relevant. But I would argue that maybe document 1 and document 2 is probably the most relevant. So then we started looking into doing some things a little bit smarter. So here's a nice flashcard from Chris Alvin, where this is basically term frequency and IDF. So basically, instead of just considering if a word just occurs, maybe consider if the word is a common word, if the word is common in the corpus. So this is just 2 ideas that are combined together, and instead of just like a Boolean score, you have this combined score. And there's one small problem with this. You see that we are just considering term frequency and IDF. There's no like scaling factor or dampening factor. So then this is the story detail of DM25, which powers a lot of databases like Elasticsearch and Solr. The formula looks a little bit scary, but if you notice that here we have like the IDF piece, which we saw previously, but we have some extra dampening factors. We have the term frequency, but then we have like some dampening factors considering like the length of the document. If you also see here, like here the original term frequency will just continuously contribute, but in this formula you kind of dampen it after like let's say 20 tokens. So there's a lot happening in this formula, but I just wanted to show that this is a model that is used in like databases like Elasticsearch. Elasticsearch is an open source search engine. It powers a lot of companies' search stacks. Not only does it support like boosting, it supports things like filtering, autocomplete, and it builds like a distributed search system. And so just some slides on Elasticsearch, assuming you have like a corpus for like an e-commerce item that has like a title, description, brand, this is how you might match it to Elasticsearch schema, where you can say fields a text, whether something's a keyword, whether something's a numeric. So you can index kind of a complex document. And if you have a query like Nike shoes under 100, not only can you do like this Boolean retrieval, so here we're searching for the query, the tokens Nike shoes under 100, we're looking in the title and the description. If it appears in the title, we are boosting it by a factor of 2. We are filtering if the brand intent is met. We are filtering if the price is less than 100. So you can build a very powerful retrieval system with something like Elasticsearch. And in a production system, if you have like hundreds or millions of documents, Elasticsearch allows you to basically shard the corpus. So instead of searching like one large instance, you're basically splitting your search across multiple clusters, multiple nodes in a cluster. So that is token-based retrieval. And then the next era, and there's a lot of work that happened here in learning to rank. So let's say you have your query red dress, and on the left-hand side, you retrieve these 3 items. You all have red somewhere, but the most relevant item is probably the last item. So it didn't come in the right order that you probably expected. So what you do is you feed it into a ranking model like XGBoost or LightGBM. And what you consider this time is like features inside your query, like maybe extract the product type. Does the product type match the item? Does the color match the item and the query? Things you might consider from the item level is like, is the price like a reasonably priced item? Is there a lot of customer reviews for this item? And other things you can consider in the context is like, what are other queries that the user has searched in the past? So you can consider all these features and then kind of re-rank it and get your final ordering. So I would say in production, most companies kind of use like the BM25 approach plus the learning to rank and build a pretty powerful system. But there's still one issue with like the token-based approach that we looked at. It will not solve like if there's a lexical gap. Right? So COVID, coronavirus, Omicron, they all kind of mean the same thing. But with just a token-based thing for COVID, it's not going to really match coronavirus. The token-based approach will not solve like ambiguity. So depending on your corpus, the same word can mean different things in a different context. And the pure bag-of-word token-based approach doesn't consider position, right? Riverbank versus bank river, it means different things. And like, the bank river is, you will never see that in a normal English sentence. And definitely, in the last example, like she will park the car so we can walk in the park. We have the same token appearing in the same sentence, but meaning different things. So that's all I wanted to talk about, kind of token-based retrieval. Let's kind of take a look at the first lab. So if it's easier, there's a Jupyter Hub environment, hub.np.training. If you want also the repo, there's a bit.ly link for that, or you can scan the QR code. Just making sure, like, was everyone able to get the environment spun up or with any issues? The environment is just basically having this repo clone. So all the notebooks that we're going to cover are inside this section here. And also the slides that we're covering are available here if you want to revisit the concepts later. So let's take a look at the notebooks that we have today. So the first notebook that I would like to take a look at is, I didn't mention the data set that we're going to be using today. So there is a company, Unsplash, that has provided about 25,000 images and like captions. So you have like a photo ID, a photo URL, and you have a description. What we're going to try building today is, given a query, can we build a search system that retrieves relevant items? So there's about 25,000 images here. So let's take a look at the first notebook, 01 EM25 Elastic. Let me just duplicate it. Feel free to run this or look at the rendered output.
Sorry, how do you import the dataset?
Oh, the dataset is already loaded in this environment, so you don't need to do anything.
Doing the environment on my phone, how do I?
I think like for this session, like if you could just visit the Jupyter Hub environment, but I can help set up for this one. Yeah, sorry, I wanted to make this kind of like practical. So there's a lot of dependencies and libraries and data. So just might be useful today. So it's just hub.np.training and just authenticate with your GitHub. So let me just clear the output here. Hopefully it is large enough, and let me just let it run. So just the class imports. I have a Hugging Face data set rendered of this data set. So what are the columns that we have? So we have like photo ID, photo URL, caption. We'll mainly be looking at the photo URL and the caption. So this is what a sample record would look like. Here is the description that we're going to be using. So for this image, there's the description: women exploring in the forest. As part of this environment, there's already an Elasticsearch cluster already set up. So so it's just localhost and port. Briefly, going to talk about tokenizers and like, so we saw that example about how the kitten playing example, how some of the tokens were stemmed. So let's just look at Elastic's.
Before you start tokenizers, we have plenty of time, so you can actually get some feedback. If there's any questions.
Oh yeah.
If there's any questions, it's super fast.
Yeah, apologies for that. Yes, sorry, I moved a little bit fast. So this is the first section about like token-based retrieval. So if there are any questions about the previous sections or as we go into this notebook, please feel free to bring it up. Elasticsearch is like a production-based system. So it has some like default options for how do you tokenize, how do you stem. So if you have a query like, an HTML tag, Elasticsearch is built on this thing. So you have like some HTML tags here. There are some built-in tokenizers. If you the same thing, like if you just want to tokenize on white space, or if you want to use a default tokenizer. So one thing, if you notice, the white space tokenizer, it doesn't really deal with like these HTML tags properly. The standard tokenizer parses them correctly. So one thing I wanted, so the tokenizers and analyzers, but don't want to spend too much time here, but one of the analyzers is the stop words. So if you see here, like original query had like Elasticsearch is built on top of, but with this stop words, is on, they just get removed. Because most of the time, they don't really add much value in your query. Yes?
Would it be possible to zoom in?
Yes, apologies for that, yeah. This is better.
Is there any, so what kind of tokenizer is this? Is there any way to define this thing? Is it white space tokenizer?
Yeah, so Elasticsearch has some built-in options. So like there's the n-gram tokenizer for character-based. There's a standard-based tokenizer where Elasticsearch has some default options. And you can, of course, define your own tokenizers. It also has tokenizers for different languages. So it is pretty powerful for your standard use case. Yes?
And just compare this to like other tokenizers that would use
yeah, like so NLTK and like Spacey has some good options there. I think like for the English language, like the standard things like kind of breaking on white space, kind of dealing with HTML tags. Like I think in this case it should be comparable, but obviously like Spacey and NLTK have like much more richer models. Yeah, so we're just going to, in this notebook, let's just use the default tokenizer and just let's try to see what results we get. So I have this helper method using the Python Elasticsearch client. I'm creating an index with a name that's fast. I'm telling Elasticsearch to create 3 shards. So our 25,000 documents will be split into thirds. And then if I give a data frame of documents, I'm just going to iterate across it and just kind of clean up some things, like create a document ID, remove any empty or null fields. Once I have my Elasticsearch index created, I just call client.search. I tell it I want to search for the field. I want to search in multiple fields, but in our case, we only going to be searching in the description field. And how many results return. And Elasticsearch will do that BM25 formula that we saw before. So I created my index here. You can see some settings that Elasticsearch exposes. So this is the index name I created. This is the number of shards that I created. It has 1 replica but 3 shards. And we have about 25K documents. The inserting step, yes, in the inserting step, we inserted 25K documents. We inserted about close to 3,000 documents per second. That's a pretty amazing, that's a pretty good insertion rate where Elasticsearch is like scanning, tokenizing, doing all this processing and updating the index. So it's pretty fast. And since we had 3 shards, we see shard 1 has about 7,500 documents. The second shard has about 7,200 documents, and it's about 9 megs per shard. Yeah, so let's see how well the result is actually performing. So in Elasticsearch, you can retrieve a document by the ID if you need that. But in our case, we're going to be retrieving. We're going to try to do a query-based retrieval. So let's take the query, 2 dogs playing in the snow. Let's see what results are returned. So this is like the raw Elasticsearch payload, giving you metadata about how many shards there were, how many items could be in a possible recall. It has this source field where if you want all the metadata that was inserted for a document, let's see, and there's a score, how relevant this document is for us for your query. Let's see, and Elasticsearch is built on that BM25 formula, so you can easily tell it like, hey, if I tell explain equals true, you can see why a certain score was given for a document. So if we consider this first document, I think it was like 2 dogs playing. So the title, the description for this first document was 2 white dogs. And we see that in the details, it tells you, I'm giving this a boosting score of 2.2 because there's the field 2 inside this document. I'm giving score of dogs. For the token dogs, I'm giving it a score of a boost of 2.2. The IDF value that we saw is 6. How many documents contain this term? 9. So it gives you all these great debugging information. So it is an explainable kind of model. Yes.
So the score is BM25.
Varying the BM25. Yes. So, but let's just look at the results that are returned. So this is the results that are returned for 2 dogs playing in the snow. Why did this come? So in this document, we're looking at the description that the author has provided. So they're not really feature rich. So this one is 2 white dogs. It's not, for me, this doesn't really look like the best image, but I can see that, okay, 2 dogs, I don't see playing or in the snow anywhere here. This one, 2 baby elephants, okay, they're playing, but it's not dogs. So you see that just based on pure token-based things, you could see some slightly irrelevant results. So you can boost some Elasticsearch query options like, matching phrases, tokens that match, that appear together, but there's still some gaps here. Let's just quickly look at some examples before we switch to the next thing. So, boy and girl on beach. We see girl, we see beach, but this is again maybe not the best image. But again, based on the description that's provided. And just one last image in this thing here. If you look at, kind of a little bit meta query that someone has shared, light at the end of the tunnel. This is at the end of the tunnel, but it's not really capturing that context. So BM25 is a very strong baseline. We saw how quickly it gets to insert. It takes 4 milliseconds to retrieve a result on a very small node, or a single node. So it is a pretty strong baseline. Let's look at kind of some modern approaches to kind of solve this problem. And this section, the embedding-based retrieval, is a little bit dense. So please feel free to ask any questions that might be there. Again, the slides are available in the assets if you want to follow along, or just look ahead or look at it later. So what do we want with embeddings? Embeddings is just a way to represent a word or a concept in a vector. So what we ideally want is, words that mean the same thing, like car and automobile, to basically have the same representation. We want documents that talk about the same thing, like ice cream was great or ice cream was the best, regardless of the length of the document. We want them to basically have the same representation. What was the first approach to kind of build this kind of word or concept-based embeddings? Word2Vec was released in 2013. The idea was you look at a sequence of words, and then given a word, you look at the context to the left of it, to the right of it, and then you try to build this very simple network that tries to learn the weights to predict that token. This is one of the models of word-to-vec. It was in 2013, and people have extended this word-to-vec idea for sequences. So this is from Instagram that they shared in 2019, where basically if you look at accounts of the images that people have looked at, you can try to learn embedding for the accounts. In word2vec, the previous thing they're learning like word similarity, here they're learning account similarity. You can also expand this to other things. So Grubhub expanded this to like restaurants. So they look at all the restaurants that people have interacted in a session, and then they try to create like a restaurant-based embedding. And this was actually a talk that was done in 2019 in PyData. You can watch the recording if you're interested. So word2vec is a pretty powerful approach, especially if you have interactions either with text or like sequence that from your logs. But these days, especially for NLP or just text, people use word, right? Given an input, Bird has a tokenizer. It might be a bit small here, but if you look like plain, it gets separated into like subwords, right? There's play and then the pound and ing. So there's a subword tokenizer that Bird is built on top of, and as part of your training and as part of your input to your model, Bird has like position embeddings that you feed into your model. So Bird is really powerful, so don't want to talk too much in the details of it, but just wanted to show that Bird kind of considers position. It will learn context a little bit better. Bird, the base model of Bird supports up to like 512 tokens, and it has 12 encoder layers, and after each encoder, there's an embedding that is available, and you can use those embeddings. Bird gives a word-based embedding, you can kind of pool all the embeddings together and kind of get like a sentence embedding. And this is one good approach. Bird solves many of the problems that we have kind of seen with like kind of just token-based things. Like it learns a contextualized embedding. It captures position, so it has a good idea of language, and it is trained on a very large corpus. But one of the problems with using just Bird as is for like building a retrieval system is Bird by itself doesn't really capture similarity really well. So we need to have a model that kind of makes our model learn similarity better. So how do you solve this? One way is a network called cross-encoder. Basically, the idea is you feed both, let's say sentence 1 and sentence 2, you feed it into Bird. Bird uses its like attention mechanism, and it outputs a score whether these two items are similar or not. This model gives very good results, but for a search system, if you use a query like this to compare with the entire corpus, it's not really efficient for information retrieval purposes. So the approach that many people use is this two-tower model. So the idea is, you have your sentence 1, sentence 2, you feed it to your encoder, in this case it's Bird, you pool the embeddings. While the model is there, while it's being trained, you're telling your model to kind of learn if sentence 1 and sentence 2 is similar. So this is the training task that you're giving for your model. You can use the same Bird model here, or you can use different encoders depending on your domain. But for this use case, it might make sense to use the same encoder. So if you have a lot of data where you have like 2 pairs and you have a score, you can use this to kind of learn similarity, similarity-based embedding. Maybe I'll take a pause here to if any questions have. Going all the way from the simple word-to-vec kind of embedding to kind of going to the sentence-based or model that kind of learns similarity-based embeddings. Yes?
So what about an item which has a name which is I invented, right? You know, it's not in the corpus, but just so how do you?
Yeah. So I guess here, like if the item tokens are not in the corpus, like if hopefully like the subword tokenization would solve some of it, but definitely if the tokens are not in your corpus, like you might need to train and tokenize on your corpus. Yes.
Can't you expand a query based on synonyms between words? You get the synonyms from something like word-to-vec.
Yeah. So that's a good point about like synonyms. So even in the previous approach with tf-25, like we can probably get good results by using synonyms. Here, with like word-to-vec, you know, if you train it, you can enhance the query that the user has typed to kind of use the synonyms to kind of retrieve relevant results. But I think one of the nice things about like training a model that is like this where you have two similar concepts and you don't explicitly define, like the sentence embedding should capture the idea of synonyms pretty well if you have a large enough corpus. Yeah, so we have a small lab to kind of just play with some of the results that we saw with, compare it against the tf-25 approach by using a pre-trained model that was trained with the sentence similarity task. So if you take a look at notebook, so there's the notebook here called Dense Retriever Milvis. So Milvis is like a vector database. We'll talk about it a little bit later, but let me just close all the notebooks and duplicate this notebook. So there's a nice library called Sentence Transformer. I'm just going to click run all this because it takes some time. So there's a nice Python package called Sentence Transformer, and in the Hugging Face Hub, they've uploaded several models that were trained on this this bi-encode architecture that we saw. So this model was actually trained on 1 billion sentence pairs taken from a wide variety of data. So Reddit comments, Wikipedia answers, and a smart stack exchange. So it's trained on a very large corpus of sentence similarity, you know, title, abstract, duplicate questions. So it should have a good understanding of like similarity. So let's just use this existing model as this. So this model, given a sentence, it would give you a 384 dimensional vector. PyMilvis is the Python client to talk to this vector database that we'll be storing. So if I import this model in Sentence Transformer, you see the transformer, and then you have this pooling layer that basically takes the intermediate embeddings and then returns a 384 dimensional vector. So this is like a Stack Overflow question here. We see that when you give it to the model, like it does do tokenization. It has like this attention mask. Some of these things from BERT you see. You have like the intermediate token embeddings, and then you have the final sentence embedding. In our case, we're just going to be looking at the sentence embedding, which is 384 dimensions. Yep. So the token embeddings, in our query there's 30 tokens. So Hugging Face has this nice library, auto tokenizer, so you can kind of see the intermediate results here. Kind of the subword tokenization that we talked about. It doesn't just use the token separated by white space. So in this case, since we're just looking at the results, I will directly go to that. Let's see. So Milvus again is like an open source vector database. So here's just some examples of using the client. So if the collection exists, we can drop it. We need to provide. Oh, sorry, what is it? Maybe it's right this out here. It's going. Let me just go here. So. So one thing is compared to like the BM25 approach, like generating an embedding for like 25,000 documents, like on this instance that we have, will take about 3 to 4 minutes. So 25,000 is pretty small. This is not using a GPU, so that's why it does take some time. But let me just go. Yeah, so this is Milvus specific. So Milvus again, it's a vector database. It stores its metadata in MySQL. When you create a collection or a document, you need to define, the field types. Elasticsearch is a little bit smart about kind of inferring these types automatically, but for these vector databases, you do need to specify the schema beforehand. Specifically, you need to specify like the ID to identify a vector, and you need to specify the embedding and the size of the embedding. Let's see if this is running. Still some stuff. Okay. Mainly I want to show the retrieval results. So let's look at for the same queries that we saw before, let's look at the results that we saw. So I have a data frame. I just call Milvus.insert. It gives me how many documents. Inserting is pretty fast. It's just computing the embeddings that are pretty slow. We'll talk about this piece about the different types of indexes in the next section. Yep. So there are like some parameters that you can pass when you query. Again, we'll talk about this in the next section when we specifically talk about the type of index. But once you have your database, using the Python client for Milvus, you just give it a vector. You tell it which field, which embedding field you want to search for, which fields you want to do. So the API is very clean. One thing I want to highlight here is that you see here it took about 206 milliseconds. If you remember in the Elasticsearch notebook, it took about 5 milliseconds. So this is a pretty expensive operation compared to like the BM25 Elasticsearch. But let's look at, for this performance degradation, are we getting good results? So, so this is the query and results we get for 2 dogs playing in the snow. You see in the description, so here we are embedding the description field, right? So we are embedding brown and black dogs running on the snow. I think this result is pretty good. It's understanding running and playing kind of matches in the same space. So this result looks pretty relevant to me. And dog playing on the snow, maybe not 2 dogs, but this is a very small corpus. So the results may not be the best. If you remember this query, when we looked at BM25, it was not the best, but if you look at the query for boy and girl on the beach, like children, it kind of matched, matched that query intent to this description. So I would say it's doing a pretty good job, definitely better, much better compared to the BM25 approach that we looked at. And maybe let's look at the final kind of abstract kind of example, light at the end of the tunnel. Again, the description is just like light keyhole, light direction. I would say like these things, at least for me, are more relevant than what we saw in the DM25 approach. Yes?
So this retrieval is based on the description only, right?
Yeah, only the
So
description.
why you needed that data structure for all the photos and
Yes, yeah. So I do talk about this a little bit later, but the general idea is like when you do retrieval, it's not sometimes just enough for like vector similarity. Sometimes you might want to say like I want photos that are similar, but like the license is open source or something, or like it has at least 1,000 views or something. So you need your vector database to be able to support those things. But that's a great question. Yeah. Yeah, I mean, this is there was a lot we covered with embedding and embedding-based retrieval, but I just hope if you were able to follow along with this notebook to show like how easy it is to kind of get started with the existing embedding, how easy it is to embed, how easy it is to use like an open source vector database like Milvus and use the Python client insert and find results.
Is there any way you can use this embeddings with Elasticsearch?
Yeah, that's a good question. So Elasticsearch in its most recent version does support vector database, I think like version 9.2 or so you can use it. So it has been recently supported, yes. Yes.
So the Milvus is like a database of embeddings of text already on web pages, basically. Is that right?
I mean, here we embedded like a description. So we inserted metadata and we inserted embeddings for text, but you could have inserted like image embedding or like some joint embedding.
Right, but I mean, is it? I get what it's doing with our prompt to docs, but I mean, is it already named embeddings of a catalog of website text like metadata from this? That's what I mean.
Oh, yeah, sorry, I just came over that field a little bit quickly. So the 25,000 photo collection that we saw, like I did create the embedding from the model. So yeah, from the Hugging Face dataset, I just call model.encode with this model, and when I insert it in Milvus, we insert the embedding of the description. But this embedding could be like the word to vec embedding that we saw before, or like image to vec or rest to vec. Yes.
Yeah. So does your process, is your process capable of leveraging the embedding space to actually index the vector database so that you can accelerate retrieval depending on whichever kernel you'd like to reference between the similarity of the vectors?
Sorry, could you repeat the question again? Sorry.
So like, do you know how you have an embedding space and depending on like Sorry, thanks. Do you know how like when you have an embedding space and depending on like whichever like when you are comparing sentence pairs, you're generally going to have like some form of an inner product that's casted, but in this case it's going to be cosine. Yeah. Is there any way that you can actually like index or shard or search based off of like how close they would relate to each one of those, so that you can retrieve the information faster, or maybe like you could have reverse intent, so being able to like more so say, oh hey, what if I want to find something that's not this? Would that be a built-in feature of that vector sort?
So in the next section we'll talk about like building like the vector database to make it faster for retrieval, like kind of sharding and stuff. But the similar thing is not an easy problem. So
yeah.
That's not quite there. Yeah, that's a great question. Yeah, I think I'll let my focus center Ravi take it from here. Yeah.
Before we go into the next section, do we have any issues with the development so far? So hi, my name is Ravi. Thank you, Nidhan. So far, I think what we have looked at is what are the issues with BM25, and if we go to the embedding-based approach, how can we find out similar text? Right? We have something. We have a corpus. We have all the documents. How do we do a better search using embeddings just based on text? So before we go into like different use cases of that, there's one thing that I want to cover. So one thing I wanted to cover was how do you train your models? So you're doing nearest neighbor search, and you're trying to train your embeddings. But one of the main issues that happens when you're training your models, your embeddings, is what kind of data are you using? So it's very easy to have positive samples. You know what is similar to what. And the question that you have, right? How do you find the dissimilarities? So it's not always easy to find dissimilarities, but you still start with something which you know that Apple is not similar to orange in a context, but it could be, but it's still not similar. So we call them negatives, right? So it's very easy to have positives. You can still start with some negatives. But how do you generate more negatives as you go along? So this is a concept that was there in online learning. It's still there, which is called as hard negatives. So basically, this is what we call it like easy negatives. So you have the anchor. Anchor is the query that which you're searching for, and you have positive samples and the negative samples that were there. And what's returned is a positive sample, and if the anchor query is similar to the positive sample, and that's what you're looking for. Now the second case is this, where positive and negative samples in your corpus, they are very closer to each other, and the anchor query, the query which you are searching, is still very far. Right? So we can still call it like semi-hard because it's still closer to the positive sample than to the negative sample. But this is the other problem, which is the anchor query, which should be similar to the positive sample that you're looking for, but it seems to be similar to the negative sample. And when you do inference, when you do testing, that's the kind of data that you get. So the idea is, when you have these testing data, can you feed this data back into your model for further refinement and to further optimize your embeddings? So these data points that you're selecting, these anchor queries, they could be called as your hard negatives. They would be called as your hard negatives. So far what we've seen is text-to-text searches. You have a text corpus and you want to search for something using a text query. But as the e-commerce and other systems are growing, you don't only want to search for text, you may want to also search for vision or image-based solutions. So one of the architecture that recently got popular because of AI is the flip architecture, where you have embeddings for your text and you also have embeddings for your images, and you try to train them together for a function, and you try to create those embeddings such that the two embeddings, both of them, vision and text, they are similar to each other. So that's what happens in Flip. But as you see with other different systems, you don't have to stop with the text and image. You can extend this to what Google has done for their App Store. So if you search for, let's say, Facebook app or Windows OS or something, they want to connect that to an app. Right? Now, you have all these features that you can use for the query and the app features, sometimes even the user features. So all of these things could be used to create two embeddings that you see at the end before the dot product, that is the query embedding and the app embedding. And you can train this architecture for using cross entropy for an optimal function that you try to optimize. So if you're trying to optimize for these users searching for something and they end up clicking on or downloading those softwares, those apps, then you can use these to train that. And eventually what you get is two embedding. One is the query embedding and the app embedding. And you can use these two embeddings to do nearest neighbor search to find out if somebody searches for this, then what is the app that is similar to this. Okay, so we're going to have another quick lab to basically learn about the similar kind of experience that we've been seeing so far to the query-to-query searches, but we want to go to query-to-image search and see what kind of results we get with that. Yeah, so we will be using a clip model. So clip model is trained for finding embeddings of your images given a text. So I quickly want to show the results because there's nothing fancy about it. It's something similar to what we do for text. You have a model, you put your corpus into it, and then you train it. Because in this case, we're using a pre-trained clip model. So this is the kind of result that we see when we use the query, two dots playing in snow. I think this was a similar thing that we were seeing earlier with the text embedding as well. So, but this is the second one, which in this case we see that friends will be friends. So there is no text similarity between what we are searching for. But if you look at the image, this is the image which is similar to the previous image. So not only it's similar to these kind of approaches tells us that not only this is similar to the text that you're searching for, but these two images that we saw, this one and the previous one, they are also much similar to each other. So, and then we have this one set and further down and so on and so forth. And this is the other one, which is the search field that we have is going well on the beach. And if you look at this image and the title of this, it just says white sands. Has no context about the boy or girl or beach or any of those things. But just by looking at the image embeddings, you can tell that this image has something which translates or which is similar to the query that you're searching. And I think one of the examples that we were looking for, which was like at the end of the tunnel. Again, the same thing. It says gateway to heaven, but I don't know where it is leading to. But it still looks like what you're searching for, just from the image in this case. Before we go to the next slide, is there any question about clip model?
So how was it computing the similarity between two images when descriptions are not similar?
Yeah, so let's go back to how is doing similarity between two embeddings. So we have two vectors, they could be of dimension these, and we're trying to find out Euclidean distance between them. Or you can do dot product or cosine similarities, all the things, and we're trying to find out how closer these two embeddings are. And the closer they are, the distance between them, they are similar. And the reason why we are sure about it, because when we were training these embeddings, be it the clip or the other file encoder that we were talking about, the reason why we're sure is because that's what we were training them for. We were training them the pairs that these are similar or these are dissimilar. So the positive samples and the negative samples. Any other question? So let's go more into the question that was recently asked, what was how are we doing it, and what exactly is happening here, how we're searching for something. So we can think of all these dots here as our corpus, our search space, all the vectors that we have generated, be it the image vector or be it the text vectors. So we have this 3D or n-dimensional space, and then the one highlighted is our query vector. And the basic idea would be try to find out distance from this vector to all the vectors in the space and see which one is the closest one. So that's what we call it as flat index. We try to search for this vector against all the vectors, right? And the issue with this vector is, or this approach is, it's not optimal. It runs at order of n because you have to compute it with all the data points that you have. So the other solution, or the optimization that we built on top of it, which was the previous question, can we do something about it rather than searching for everything? Can we do something meaningful about it? So one of the approach is, can we do an inverted index? And that would be, instead of looking, so this is our corpus, right? We haven't even started looking into it. But this is our corpus, and we see that there are certain clusters all over the place, right? So the idea is, instead of, if I know that this cluster has a property and this is over here and this cluster is over here, and if a new item comes in and it tells that that new query is similar to this cluster but too far from this cluster, can I use some of these learnings to only look into this cluster, right? So to do that, we have to first create, I would say, a data structure which tries to find out the centroids of all of these data points. So, or all of these clusters. So this cluster could have a centroid here, and this could have a here, and so on and so forth. And then, once we do that, this is the kind of architecture or data structure we get. We are not eliminating all the data sources, they are still there, but we're just adding another layer which says that on these graph, these are the, or on this data source, these are the centroids. So we're not optimizing more on the memory, but we will be optimizing more on the retrieval. And how that happens is this. So this is our source query, or the anchor query, or query that we are searching for. And what we do is we find out the distance from this query to, let's say, all the centroids. And it tells us that this is closer to these data points. So, and then if you're only looking for one, we could probably find out the similar one. Now, how do we, so there are certain features, or I would say certain properties or parameters that I used when we search for these kind of solutions. One of them is drop. There is one that I missed. It's called as nlist. So in this, so nlist tells us how many centroids do we want. So if you have n elements, and we want to have n centroids, we're basically just building this flat index. But if you want to reduce nlist from n to a smaller number, we are trying to reduce it. We are trying to create more, or I would say, smaller clusters, a fewer number of clusters. And with that, we can also determine how many clusters to drop when we are looking for data. So again, if both are n, then we are basically using the flat index. So most of the indexes that are built, they can be categorized into three basic buckets. One of them is the tree, the one that we looked at earlier. The other one is hashes, where you can hash certain things, similar to the dictionaries. And the other one is graph. So this is one of the, I would say, index that is used these days in mostly all the search systems or all the nearest neighbor systems. And this is a graph base. So what it does, instead of having all the trees or all the pair points thrown around, it tries to find out all the common items in each layer, and then it has one entry point from this layer to the next layer. So it's kind of like a skip list approach that's there in the data structures, where you each layer tells that I can go, if you can go to the next one, it skips all the elements because they are similar layers. So it's something similar that this architecture has I would say, copied from the skip list architecture, where it tells you how quickly you can go and find it. So if you trace this path of the query vector, every graph or every index will have an entry point. This is where you have to go in, and then you try to find out the nearest one on this layer, and then you go further down because this has a connection here, and then you find a nearest one here, and then you go down, and then you find a nearest one here. So this is similar to traversing through a tree, but it's exactly not a tree. It's not a feather. Any questions here? Okay. So these are some of the benchmarks that we can talk about. So as we were talking about the inverted index, when we were creating the clusters, we saw that if you have n data points and you create n number of clusters and you want to search for all the n clusters, basically you are doing a flat index, which means you are saying I want the equal of 1 because nothing can be better than that. So if you look at this line, what we can see here is that as your drops increase, you're increasing your recall, but then you're reducing the number of queries that you can process per second, because it's going to be much smaller, and this is going to be like a flat index set on the blue line. So that's what it is. But the advantage that we see with H and SW, or the hierarchical navigable, small words. So what we see that is, though we have created a bigger data structure there, because you have graphs, you have different layers, and you have traverse through them. The advantage that we see with them is when you are looking for a larger data set to traverse, and you are looking for a recall of 1. So what we see here is that not only at the lower recall, you can process multiple queries. But if you're looking for very high recall, this approach is very similar, very close to the brute force assessment. So if you're a little bit relaxed in terms of the recall that you're looking for, you can use this layer, and this layer performs much better than the recall or the flat indexes.
So the recall is how many?
So recall of 1 would be you're looking for 2 dogs playing in snow, and you have something which has 2 dogs playing in snow. Let's say you're looking for all the text that has 2 dogs playing in snow, and it returns you everything. But if the recall is less, then it means sometimes it may throw you dogs playing in snow. Just because if you look at the centroid that we created here, so it's possible that when you're probing it, you might be probing this one and get your result, but you could have you could have been nearer to this centroid or the point here in this cluster, but you could probably get one from this cluster. The cluster was close.
So basically, how many clusters you need to scan?
Yes. So if you limit your clusters, you are basically giving up on the recall, on the quality. Yeah. So recall is the number of items that you want to return, which should be the one that you want them to return.
So are you maximizing recall so that you can address precision at the classification layer, or does this address both of them?
So
in terms of ranking?
We are optimizing recall for what?
Are you trying to maximize recall here so that later downstream you can address precision, or are they being addressed?
Oh, no, this is basically, this one is the recall of each model itself. So it's not about each layer.
Oh, got it. Okay.
Yeah, this is about the whole design itself.
Okay.
So basically, you're looking for, so in many systems, sometimes speed could be more of interest than the actual recall. You may want some good result to be out there, but not exactly wait for the perfect result to be found. So that's why number of queries that you can process per second could be of interest to you than the actual result. So if I'm searching for, let's say on Google, I'm searching for the nearest restaurant to me, and there are 2 restaurants which are like equidistant from my place, and if it gives me one instead of giving me both, I would still be okay with it. So that way I would want a system where I want the queries that can be processed faster. But the other thing could be if I'm looking for a hospital and there's a hospital which is like closer to me, and instead of just it gives me a hospital that is a little bit away from me, maybe even like 100 meters, I would want it to be better on the precision and maybe get that result, like instead of like skipping the result. So it depends on what you're optimizing.
So you're building this inverted index based on the label images that we have?
So inverted index is built purely on the embeddings that you have. So just based on the embeddings, you're trying to create clusters, ignoring the label that you may have on those embeddings.
The full corpus.
Full corpus, yeah. So you basically start with full corpus. You start with everything that you have, and then you try to find out the centroids. All right. So there are a lot of, I would say, A&M options that are out there. We, in our practice, have used Files and those. So these libraries or these packages, they can help you put your data into them, your embeddings in them. And they also help you find them. Some of these they also support like multiple indexes. Some of them have all the indexes that you're looking for. Some may not have those that you are interested in. Some could be, so basically what are the parameters that we use to identify which one do you want to use. So one is the manage or self-hosted. Some of these you can host on your own environment or your own desktop or laptop or whatever you want to. The second one parameter would be performance. Which system gives you better performance on a given hardware or at a given recall precision that you're looking for. The third one is very important. It really goes back to your use case, which is how frequently do you think your corpus is going to change? So if you have a system where your image search system, something let's say for Instagram, and they want to keep on updating those images, then maybe a particular solution could be of interest. Where it's also possible that you have documents that you have already, that you know that they're not going to change as frequently, so you can use the other system. So there are some systems or some indexes that are good for create them once, dump them, and then you can build them as much as you want. So those are three important ones. And then we also have sometimes conditions that you want all the items that are similar to this vector, but you also want them to have some secondary criteria to meet. So for example, if I'm looking for the image that we had, which is show me all the images where in which there is snow, but it should be day, right? So you're looking so because you're adding that condition there, so you're looking for all the images, and then you want to add a layer of filtering there. So some systems may support it, some solid systems may not support mechanical filtering. So that's the one. And rest two, I would say they're mostly based on, the last one is mostly based on the plugins. Some have some plugins that you want to use, some may not have those plugins. So this is the concept of filtering that we were talking about. I think I should have moved the slide above. So what we were talking about earlier was you have all these data points in your cluster. Right now, let's say we look at flat index, just to explain it. And then we are looking for something, or we have a query vector. In this case, let's say this red one is a query vector, and we are saying give me the closest n number of candidates. But they should meet a certain criteria. And that criteria is not part of our embedding, right? So what this filtering is supposed to do is first find out those nearest neighbors. Instead of 10, maybe it will find 50 neighbors. And then it will parse through those, all these neighbors that it has found out, or the candidates we will call them, to make sure that it meets those metadata filtering that you're interested in. So sometimes the reason why it can be of importance is how many data points that it should read to apply those filters. One of the strategy could be, or the brute force would be, read everything that's out there and then apply the filter, which is not optimal. And the other one could be just read only 10 and then expand, next 10 and next 10 and next 10. So some systems are optimized just for applying filters there. So most of the e-commerce, you have those cases where you have a query, and on top of the query you're saying, okay, I'm looking for something like this, but it should have these conditions as well. Something that can be shipped faster, something that is below this dollar, and something like this. So these criteria can become important when you have systems where metadata is also not just the raw code. Okay.
So does it apply that filter before it uses the hierarchical?
Yeah, so it tries to first find out the candidates for you and then apply the filter. Right. I'm not sure if there's a system that does the other way, because you first want to find out your neighbors or your candidates that these are closer to this query, and then you want to apply the filter on top of it, because you're saying, I'm looking for images or apps or search items which are similar to this, but then on top of that, I want this condition to be true. Right? So I would say that, or I would expect that the priority of query match should be higher than the metadata match. Yeah, and this is, I think, what we were discussing earlier, that you can do hybrid retrievals or full retrievals. So Elasticsearch supports both, Elasticsearch and Westpath, these two systems support both of these. Okay, so we have a quick lab to look into. So what we're going to do in this lab is we will build an ANN index using all these libraries, and then we'll try to do a search on that index. So the notebook that we're using is the 4th notebook in the repo. Okay. So yeah, I think at this point, if you want to open the notebook and you want to go through it and try some of these cells, because some of these are like basic, which is we are loading these libraries. And for this particular example, we'll be using Files library. So Files is a library from Facebook where this is basically a nearest neighbor search system, search library where you can put in your index. While you're putting your index, you have an option to decide. You have an option that you want to use the CPU to build that index, or you want this index to be in CPU, or you want to use GPU. The issues with the GPUs is if your index is too large, cannot fit in your GPU RAM, then you may want to use the CPU. But the advantage is, in our experience, it can be a magnitude faster to have your index on GPU and search into it than having an index on CPU. So we're going to do the same thing here. We have pre-processed embeddings for the queries and the images. We will load those embeddings. That will be our corpus that we want to put into Files. So the dimension of the embedding that we have, these are the image embeddings, right? So the dimension that we have is 512, and this is where we're going to create the Files images. For this exercise, we are not using the GPU, we are using the CPU here. So as we discussed earlier, we have flat index, which is called as the default. Everything should be searched again against everything. That's the flat index. We also have IDF written in the slide, or even in the notebook. I don't think we have HNS double.
What is the strand? What is the strand?
Is train, I think it's always true for this, but I think you can train your indexes. So that's what it says. So when you are putting your data in it, you have an option of training it, and if you add more data to it, you have an option of again further training. So basically, those inverted indexes that we were talking about. So for flat index, we don't have to do any training because it's going to be flat. But if you're using any other index like inverted index, you put your data to it, it's going to create those centroids. And when you add more data to it, you again want to train it so that it creates further centroids. So the easy part here is you have those embeddings, you just go to the index, you add them, and then because it's a CPU-based index, we are not passing the GPU parameters. And once we do that, we can quickly do search. Now, what it's going to do with search is it's going to return us two elements, or two, I would say, in arrays. One of them is a distance array, and the other one is the item, the index. So the distance basically tells you what was the distance between these the query vector that you had, and the indexes that it returned, which is things are similar to your query. What is the distance between them? And the reason why distance can be of importance is you can have further rules on it that if the distance is lesser than this or the distance is greater than this, then I'm going to discard my result. So in those cases, distance could be something of very importance. So in this case, what we are doing is we're just testing. So we are just testing here if I give one element to it and I want it to return k equal to 1, just one item, what is going to be the runtime? And we can see that even on CPU, the runtime is pretty good. On GPUs, it can be, like I said, a little faster. Now again, it depends on what is the size of your corpus. This one has only 25,000 images in it. You can try with like million data points as well, but in our experience, this is still going to be very efficient. So the second time here is where we are saying search for every element that is there in the corpus and give you one element out. It basically means we are searching for ourselves in the index, right? So even for that, we still feel that the time is pretty good. And as I was saying, D is the distance vector. The first element has distance of 0. So this is the result of what we saw earlier, which is we are saying take all these data points and give me the nearest neighbor for all these data points that are there in your index, which is the same as the data points that are there in the index, which means for every vector, we should get one vector which is itself out, and the distance for that should be 0. So essentially, let's assume that all of these are very smooth, very close to 0. Some of them are not, but yes, that basically tells that it's not exactly completely trained, but this is still, I would say, pretty close to 0. Yeah, so any questions so far regarding how we are querying numbers for files and what kind of data we are getting from it? Or any other concerns regarding what we've done so far? So, if not, then we'll move forward. This is the trainable index. So again, when we are giving data to it, we want files to train the data point that we have given and create the IDF index. So to answer your question, right? So the flat index don't have to train, but this has to be trained. And if you see here, we are saying files should use distance L2. That's the metric that will be used to find out when we are doing the training, which is the inquiry distance. So what we saw earlier was when we asked files to give us, we gave one item to it and we asked it to return one item for us, and we looked at the time that it needed. It was somewhere in the magnitude of 10 milliseconds or so. But now, because of this inverted index, we see that it has created those centroids, and because of that, it's probably like searching faster. So we see that it has dramatically improved. And we are only saying that look at only one cluster to get this item. And one thing to remember here is that this is again on CPU. These systems are optimized to run on GPUs. So if you use a GPU, you're going to see much faster results. Yes, before we go to conclusion and talk about what else is out there in the market, what other people are doing, any other question that I can answer?
So is there any way to combine text versus text plus images? And also how to add like similarity between text, like if you said toddler food versus baby food, right? Yes.
Right. So basically, to answer the second question, how do I combine that toddler food should be very close to baby food? So that goes to how do you train your embeddings. So when you're training your embeddings, you have one embedding, you have one vector for toddler food, one vector for baby food. Now, let's say we use this in context of e-commerce, right? So co-clicks, or what we can see is that if customers search for this, they buy these items, and they search for this, and they buy the same item, or similar items. So that could be used as a positive, can be used as a positive signal. So that could basically tell us that if people, like, irrespective of the queries that people are using, they're buying similar products, then maybe the queries will be the same. So you can use those kind of, I would say, information when you're training your embeddings.
Good question. Just wanted to know your take when you have vocabulary gap instead of lexical gap. Let's say if you search for fancy clothes or fancy toys, do you have any ideas on how to handle vocabulary gap in that case?
Yes. So if something is not part of your vocabulary and how your tokenizer is going to handle that. So one of the, I think, within what you said was, if you don't have it, you can train them, right? So different systems have different ways of handling out of vocabulary cases. Some try to put them as a default one and try to use that. But at some point, you have to decide if you want to train your vocabularies or tokenizers, or you want to keep on using that. So it depends on how many out of token words or how many out of vocabulary words you have.
In the context of e-commerce, how can you boost queries based on like
contextual information around the query line. The location of the query, time of year.
Right. So let me quickly go back to the slide here. So basically, let's say we have a query feature, and then what you're saying is you want to have context features or location features. So depending on depending on whatever information you want to include in your embeddings when you're training them, because of this architecture, you have all those options. So like in this case, what we're doing is we're trying to create app embedding and user query. But if you just want to find out the similarities between queries, this could do that. So in the interest of time, I will pass it over to Lucene again to help us with the conclusion. So just some closing thoughts about production systems. So, here's an example from Spotify where they use both Elasticsearch and a vector database as well, and of course other retrieval sources. So you don't just need to use one or the other. And an example from Instagram where we talk about retrieval, but there could be multiple levels of retrieval. So in this example that they talk about, where they have 3 levels of retrieval, the first level gets from 1 billion posts all the way to 500 candidates, and then there's another model that trims the 500 candidates to 50 candidates, and then another model that ranks the 50 to 25. So you can have multiple levels of retrieval and ranking. And an example from Taobao, where again they have multiple sources of retrieval. The PM25, collaborative-based model, embedding-based models, and then they have several levels of ranking. And one small thing is, they don't just take the order that is given for the ranking score. They may have like some business needs to kind of order them in a certain position. And in general, this is a nice diagram from a developer from NVIDIA, where when you think of building like a search system, there's retrieval, filtering, scoring, and ordering. And also you need to think about the online component and the offline component. So maybe just one example of how these things might play for like an e-commerce scenario. Like if you're trying to in an item page try to show like items that have been purchased together, the retrieval layer is you have to find items that are similar. But in the filtering layer, maybe some items are out of stock. So you can't really capture that kind of information in your embedding database. And then the scoring, maybe there are items that are similar, but you might want to score them and display them based on how that specific user might interact with that item. And then from the UI perspective, even if an item is similar, maybe you want to show like items, kind of break the items based on like certain price points. Also, like maybe in a search system you want to treat like queries that are like head queries, or like long tail queries differently. But in some systems you might only use your embedding system like for tail queries, because it kind of deals with the out of domain, out of vocab a little bit better. The other thing, just it's not like an either or. One approach you can use is you can use like the deep learning model, doc to query, to basically enhance your existing document, and then add that enhanced document inside your corpus. So this is, there's no embedding retrieval at runtime. You're using like an embedding-based approach to kind of enhance the document, and these extra tokens will hopefully, like build any gap in the document. And there was a nice benchmark that was done. So there's a lot of emphasis on like embedding-based retrieval,
So here we have like our BM25, we have our embedding-based model. If you look at, there's several questions about out-of-domain vocabulary, right? So if you have a model that is trained on MS Marco, and then you search for Cora and DBpedia, you see the embedding-based retrieval is doing really well compared to the just pure BM25 approach. But what happens if you use the embedding-based approach that was trained on MS Marco and then search for like COVID or like tweets? There's definitely going to be out of vocab problem there. So it performs much worse than just a pure BM25 approach. So definitely it might make sense to kind of use that. In the previous slide we talked about expanding the document or like using BM25 and like a crossing code or a deep learning model together. You see like together they perform they perform well together. One thing just to consider the production mindset, like we saw like how fast BM25 was to index documents and to retrieve documents. In the deep learning models, we see like on a CPU increasing by a factor of 10. On a GPU, okay, maybe it might be a cost sensitive. It might make sense to serve from there. And like BM25 and crossing code, that was the last column that we saw in the previous table. It had the best results, but waiting 6 seconds for a single query might not make sense for a use case. Yeah, and that's if you want to read up more on these materials, here are some resources that we found helpful. Yeah, are there any questions that we can take at this moment? All the slides are in the GitHub repo in the assets folder, so feel free to reuse them again. Yes, so all the notebooks are here. The Jupyter Hub environment will still be online for like this week, and then over the weekend probably shut down. So feel free to try in this environment. There are like notebooks to for BM25 if you want to play with it without Elasticsearch. This is how you can do it. If you want to play with dense retriever without using Nervous, like an extra dependency, you can use this notebook here. There is a Docker environment that kind of sets up those dependencies, but just kind of playing around with it, the dense retriever and this BM25, it has no extra dependencies. I think that's